Hey, I'm Zhang from Georgia Tech, and I'll be talking about our paper PAPRIKA, Private Online Force Discovery Control. And this is joint work with Gautam Kamath, and he's at University of Waterloo, and my advisor Rachel Cummings, and she's at Columbia University. The growing availability of large-scale datasets and the ease of data analysis, while beneficial to society, has created the reproducibility crisis in science. One major reason is that the random noise in the data can often be mistaken for signals, which does not lead to valid and reproducible results. And this problem is particularly relevant when testing multiple hypotheses, when there's an increased chance of false discoveries based on noise in the data. To give the background, we're going to look at p-values and hypothesis testing. The model is we have a fixed database, and we are going to test whether the null hypothesis is true against an interesting but rare alternative hypothesis. And you can think of a hypothesis as a query with binary answers. For example, whether a drug works. A p-value quantifies the likelihood of observing these samples under the null. A small p-value indicates the alternative hypothesis is more likely to be true. Then we will reject the null and claim a discovery. And if we were to reject the null when the p-value is less than 0.05, which is a common threshold, it means less than 5% chance of sample occurring under the null. And this is a very small probability, but still up to 5% chance. And we call it rejected hypothesis is a false discovery if the null hypothesis is actually true. So when we test 20 hypotheses, we're going to expect one false discovery. And when we test 1,000 hypotheses, we will expect 50 false discoveries. And this is not good because the chance of false discoveries increases linearly. So the question is to design a procedure that takes in p-values of all hypotheses and decides which to reject. And this procedure should control FDR to be below than a threshold while maintaining high true positive rate. We also call it statistical power. And in many applications, the dataset may contain sensitive personal information, such as the JY study and clinical trials. For example, in JYs, a large number of SNPs are tested for an association with a disease. The prior work has shown that statistical analysis of these datasets can leak personal information, and it's possible to identify an individual's genotype. So we need formal privacy guarantees for the FDR control algorithms. On the privacy side, differential privacy has become the standard notion of privacy in the computer science community. So what is differential privacy? Differential privacy quantifies the information that we learn from a computation by a probabilistic distribution. Think about a database that contains 5 people and we run a private algorithm on it. And we get the output. The distribution over the output looks like this black curve. And the x-axis is the output domain, which consists of all possible outputs. And the y-axis is the probability. And we remove Alice data and run the same algorithm, and we get this red curve for the output distribution. And we hope the analyst almost knows no more about Alice data, so the two distributions should be very close. Informally, differential privacy bounds the maximum amount that one person's data can change the distribution of an algorithm's output. And formally, we see that an algorithm then is epsilon delta differentially private if all pairs of neighboring databases then differ in only one person's data. The distribution over the output must be approximately the same. except with a small probability delta. And the approximation quantified by this e to the epsilon term. And this this delta is an additive select term, and we would like it to be cryptographically small. And differential privacy is not a binary notion of privacy. You can get stronger or weaker privacy by varying this privacy parameter epsilon. A small epsilon provides a stronger privacy guarantee. And formally, the FDR is defined as the expectation of the proportion of the false discoveries out of all rejected hypotheses. And this problem can be considered under two settings, the offline and the online setting. In the offline setting, we know all p-values in advance, and we make rejection decisions at the end. In the online setting, we receive a stream of hypotheses, or equivalently a stream of p-values, and we must make rejection decisions before the next hypothesis arrives. And those hypotheses can be adaptive and depends on previous hypotheses and rejection decisions. And the only existing private FDR control procedure considers the offline setting, and it's not known how to do it online privately. And this is what we are going to solve. The generalized alpha investing rules is a classical method for the non-private online FDR control. In the algorithm, we have an initial wealth. We can test each hypothesis at a unique cost. And we receive an additional reward for each discovery. And the wealth is used to determine the rejection threshold alpha t. And the algorithm decides to reject hypothesis t if the corresponding p-values pt is less than the rejection threshold alpha t. And the alpha investing procedure ensures that the analyst always maintains an alpha fraction of their wealth, so that they can continue testing future hypotheses indefinitely. And in our algorithm, we're going to use two subclasses of the JAI rules, the lot and the saffron. As a class of JAI, the lot plus and the saffron both start off with an arrow budget, which will be allocated to different tests over time. And the wealth budget decays as each hypothesis is tested, and it earns back rewards on each rejection, except for the first one. And the main differences between the lot plus and the saffron is saffron adaptively estimates the proportion of true nulls. To add privacy, the sparse vector is a differentially private algorithm for detecting which queries in a stream have answer above a given threshold. An important quantity in every DP algorithm is this query sensitivity, and we usually use this additive sensitivity notion. And the query sensitivity is defined as the maximum amount of change of the query value on two neighboring databases, then differ in only a single entry. And this sensitivity determines the scale of noise that must be added to preserve privacy. And then for us, the query would be p-values. And we give a differentially private online FDR control algorithm called PAPRIKA. And I'll introduce several main points. It starts with saffron and use sparse vector to ensure privacy of the rejection set. Now, first of all, following the generalized alpha investing rules, it frames FDR control as an investment problem. And specifically, the updating rule of the wealth is similar to the lot plus. And we know that the wealth updating rule in the other non-private method, saffron, cannot be applied here because it depends on the data, and this would violate privacy. Here, the updating rule is only based on past rejection decisions. And second, it has a candidacy checking step from saffron. And this is a weak check if the p-value is close to rejection. The lambda t is like the loose bound. So if it's a candidacy p-value, we will consider whether to reject it. Otherwise, we will fail to reject. So only hypothesis in this candidate set can be rejected. And in the paper, we show that we cannot add noise to the candidacy checking step. So we relax the pure DP guarantee for sparse vector and provide an approximate DP guarantee by carefully choosing this lambda t. And you may wonder why we need this candidacy checking step. And we can just privatize log++. Well, we empirically compared PAPRIKA with two other versions of private lot without this candidacy checking step, and our PAPRIKA performs much better. So I'll show this result at the end. And then we have to incorporate dynamic thresholds to match the alpha investing rule, and still show this dynamic threshold do not affect the privacy guarantees. And we are adding noise that scale with the multiplicative sensitivity. And this sensitivity notion was proposed specifically for p-values, as p-values tend to have high additive sensitivity. So by using this sensitivity notion, we can treat the log scale of p-values as by using the additive sensitivity. And this is why we are considering log p values here. And the accuracy guarantees of sparse vector ensure that if a value is reported to be below that threshold, then with high probability, it won't be more than some level above the threshold. However, to ensure that our algorithm satisfies the desired bound, we require that the reports of below threshold truly do correspond to the p-values that are below than the desired threshold of t. To accommodate this, we shift our rejection threshold down by a parameter a, and a is chosen such that the algorithm satisfies epsilon delta differential privacy. And finally, there's an important detail. We require a bound on the maximum number of hypotheses tested because the accuracy guarantees of sparse vector only allows exponentially many queries to be answered accurately. So once the total number of rejections reaches C, the algorithm will fail to reject all future hypotheses. And we don't halt the algorithm as in the sparse vector, because if there's a stopping criteria, we can no longer talk about FDR control at any fixed time, because it won't be it might not be well defined. And we have an algorithm, and we also care about what accuracy and privacy guarantees it can achieve. First, it is epsilon delta differentially private, and this delta comes from the candidacy checking step, which cannot be done privately. And the delta also has to account for the shift. For accuracy, it controls FDR to be below than alpha plus delta t for testing t hypothesis if p-values are independent. And you might be concerned about this delta times t is linear with respect to t, but this delta is cryptographically small. For example, this delta can be exponentially small, so delta times t is still tiny. And it can also control a slightly weaker notion of FDR called MFDR if p-values are adaptive under the null. We also know that although epsilon doesn't appear in the bound, it plays a role in the analysis. In fact, this bound is a complicated term, which is upper bounded by this delta times the term. We also have a bunch of empirical results in the paper to empirically evaluate FDR and power. And here I'll only talk about some results on testing with Bernoulli observations. In this setting, we generate a database with Bernoulli observations, and the size of database is 1,000. And we sequentially test 800 hypotheses, and the max number of rejections is 40. And all the results are averaged over 100 rounds. And the figures plot the FDR and the statistical power against the expected fraction of non-nulls with varying privacy parameter epsilon from 3, 5 to 10. And the PAPRIKA denotes the instantiation with a constant candidate checking threshold. And PAPRIKA AI denotes the instantiation with a smarter way of setting this threshold. As expected, the performance gets worse as epsilon decrease. And it's for both FDR and power. An exception is in this picture, the FDR also decreases for PAPRIKA AI, and this is because the adaptive candidate checking threshold results in a smaller candidate set, and it leads to insufficient rejections. We also see that PAPRIKA AI performs dramatically better than PAPRIKA, and it suggests that this smarter choice of the candidate checking threshold is preferred. And we also compare our algorithms with with privacy parameter epsilon equal to 5 with some non-private baseline methods, the LORD, alpha investing, and Saffron. And this Saffron AI also denotes the instantiation with the adaptive candidate checking threshold. And we can see our algorithm tend to have more strict FDR control with some loss in the statistical power. And I promise that I'll show some results on the comparison with other private algorithms. I should emphasize the PAPRIKA is the first algorithm for private online FDR control, and there's no private baseline in the literature. Here we propose the private lot and private lot 2, and they are both other possible ways to privatize this lot ++ without this candidate checking step. And we can see both PAPRIKA and PAPRIKA AI make significantly less false discoveries than those methods, while the statistical power is almost the same. It suggests that the candidate checking step largely offsets against the added noise for private algorithms. And we have more empirical results in the paper. We have results on testing with truncated exponential observations. And we provide empirical guidance on the parameter tuning. Then is the shift parameter A. We also provide analysis of the signal-to-noise ratio and impact on performance. For more details, please check our paper online, and thank you.